Here's the answers to the multiple choice quiz from Chapter 10, Liquids and Solids. In question 1, we're looking at the changes in force of attraction that occur as water changes phase from liquid to vapor. Now, remember, a phase change does not involve any chemical reaction. There's no breaking of bonds. A phase change is a physical change. All we're doing is separating the molecules, but we're keeping all chemical bonds intact. The integrity of the molecule is the same. We're just separating their intermolecular forces, which here would be the hydrogen bonds, but no covalent bonds broken between hydrogen and oxygen atoms. No new bonds formed. Question 2 gives me two alcohols, ethanol and propanol. They're very similar. One has just a little bit longer carbon chain. There's 2 carbons in ethanol and 3 carbons in propanol. Now, both of them do have that very polar OH group, which means that there is the chance of hydrogen bonds forming in between the molecules. As long as they orient themselves properly, the partial negative oxygen of one molecule could be very attracted to the partial positive end of another molecule by that OH group. That's where the hydrogen bonding is going to occur. That's that really polar bond, because oxygen has an extremely high electronegativity. So because they both have a region of OH where hydrogen is directly bonded to an oxygen, they both have hydrogen bonds as their primary intermolecular force, just by that OH region. But then the secondary intermolecular force is always the London dispersion force. And if I were to add up the total number of electrons in each structure, the propanol should have more total electrons, so there's a greater polarizability. There's a greater chance that those electrons will not be evenly distributed around their nuclei. That gives me stronger London forces. It's not that there's stronger hydrogen bonds. They both have the same strength of hydrogen bonds. They both have one region where hydrogen bonding can occur. It's not mass. Mass has to do with the nucleus, the protons and the neutrons. And again, that the propanol molecule is more polar than ethanol. No, they have the same degree of polarity. One very polar OH group. London forces for the win. Now, kind of similar when we get to this question here. It says, which one of the following substances will have hydrogen bonds as one of its intermolecular forces? It may be the primary intermolecular force, but the secondary intermolecular force will always be the London force. Now, in order to have hydrogen bonds, you technically need the hydrogen directly bonded to an F, O, or N. They all have hydrogen, and they all have fluorine, oxygen, or nitrogen, but the third one down is the only one where the hydrogen is directly bonded to an F or N. That's what creates that extremely polar group, because hydrogen only has one electron, and it's bonded to one of the 3 most electronegative elements. So that poor little electron is drawn really strongly toward the F or N. All the other ones have the hydrogen bonded to carbon, which is slightly polar, but not as polar when it's bonded to FON. Hydrogen bonding is fun, right? This is a great question because it's not what you might expect. We've got this data in the table, and we want to know which of the liquids has the weakest intermolecular force. So they give me some substances and their vapor pressures. So vapor pressure is the pressure of the gas on top of a liquid in a closed container. So I have a closed flask, there's a stopper on top, I got some liquid inside, and the particles on the surface of the liquid just have a natural tendency of evaporating and going into the gas phase. Well, if you've got a closed container, those particles don't have anywhere to go, so these gas molecules just bounce around and collide with the walls of their container. They can also collide with the surface of the liquid, which means that some of them might go back into the liquid phase, but at the same time, other particles from the surface are going back into the gas phase. And so that's what equilibrium vapor pressure means, that the amount of particles evaporating is the same as the amount of particles going back into the liquid phase. condensation and evaporating are happening at the same rate, the same time. And so I know that if there's a weak intermolecular force, the particles are not very attracted to each other. Well, if they're not very attracted to each other, then it should be easier for them to go in the gas phase and create pressure. So at first glance, it's just as simple as the particle with the highest vapor pressure has the weakest intermolecular force. Done. But did you kind of notice that it ends up being a particle with an OH group? I mean, both of these guys in the middle, whoa, where'd she go? There it is. Both of these guys end up having an OH group on the end, which means that hydrogen bonding can occur between their molecules. Well, isn't it kind of interesting then that the one here, like the CH3OH, has the weakest intermolecular force, but yet it's going to have hydrogen bonds? And so here's one of those goofy times where this guy here ends up being a nonpolar molecule. Even if you want to sketch it, it's a nonpolar molecule and it only has London forces. But it's got a little bit lower vapor pressure. So it must mean that the London dispersion forces of C6H6 are actually a little stronger than the hydrogen bonds of the CH3OH. The reasoning is always polarizability, that there must be so many more electrons in the C6H6 molecule. If there's more electrons, greater polarizability. It can happen where dipole forces, or I should say London forces, may be stronger than a dipole or even a hydrogen bond. So wacky, isn't it? But that's always the answer. Greater polarizability, more total electrons. When there's a trend, that's maybe not what you would expect. Here's another cute question. We've got some hydrogen halides. Hydrogen with chlorine, bromine, iodine, and fluorine. And they give me boiling points. I want to know which of the other two halides, hydrogen iodide and or hydrogen fluoride, would be predicted to have a higher boiling point than HBr based on periodicity and intermolecular forces. Well, they're all polar molecules. They're all going to have at least dipole forces, but the HF is a little bit more polar, so that one's going to have hydrogen bonds as its primary intermolecular force. It's baby hydrogen bonded to the most electronegative element on the entire periodic table. So it's going to be extremely polar. I would definitely expect then that HF, because it's so much more polar, the partial positive and partial negatives will be so much more extreme. HF should have a higher boiling point. But so would HI. I mean, all three of those, HCl, HBr, and HI, shouldn't have dipole forces. They're still polar molecules. But the secondary intermolecular force is the London force. And the HI should have more total electrons and be more polarizable, which would then create a little bit stronger London force and a higher boiling point. Then we get some of these cool graphs. Here is a phase change graph. At segment S, there is obviously energy being added. I mean, the graph says it, right? There's heat being added. It's just that heat can either be used to increase the temperature or change the phase. And when I change the phase, the heat is being absorbed to overcome the intermolecular forces between, in this case, liquid particles, so they can exist in the gas phase. That takes energy, but you're not going to see a temperature change. Temperature is a measure of kinetic energy. So if all of the particles are in the same phase, now if I add heat, I'll make the particles move faster, increasing their kinetic energy and their temperature. The second choice is right. Up at segment S, we should have particles in both liquid and gas. At the beginning of segment S, it's mostly liquid, just a little bit of gas. By the end of segment S, it's mostly gas, just a little bit of liquid left. We're going to be stuck up there at the boiling point until the entire sample changes phase. And so at segment S, there is no increase in kinetic energy. That's temperature. That would be segments P, R, or T, where it's all one phase, and I'm increasing the temperature, making the particles move faster. Also at segment S, we did mention that's the boiling point, but did you catch that the temperature here is in Kelvin? And so in the AP packet, they will give you the conversion between Celsius and Kelvin. So this would end up being about 77 degrees Celsius, and that is not water. Water would boil at 100 degrees Celsius, or 373 Kelvin. This graph is actually for ethanol. Ethanol boils at about 77, 78 degrees Celsius. We have 23 grams of solid ethanol heated at a constant rate. Which of the following explains why the slope of segment T is greater than the slope of segment R? Did you kind of notice that? The slope up there, T at the gas phase, is a little bit greater than R, the liquid phase. Okay, well, whenever you're increasing the temperature, we're looking at specific heat. Specific heat is the amount of energy needed to raise the temperature of 1 gram up 1 degree Celsius. And so there's a couple different ways of looking at this one, but I was kind of looking at like the little boxes as like a unit of heat energy. And so I kind of said, if I look at a box as a unit of heat, well, in segment R, it looks like each box is about 50 degrees, but up at segment T, each box is less than 50 degrees. And so it looks then like less heat is needed to raise the temperature up 50 degrees, for example. And so then up in the gas phase, the specific heat is actually less than down in the liquid phase. I like that one. And then we can do calculations. So when we have a temperature change, like section P, R, or T, we're going to use the equation mass times specific heat times temperature change. This equation is in the AP packet. And so it's plug and chug. You've got your mass, 23 grams. Specific heat we have as 2.44. So it takes 2.44 joules of heat to raise 1 gram up 1 degree Celsius. Well, we've got 23 grams, so we multiply, and we're raising the temperature up 50 degrees, so we multiply. So it kind of makes sense. I should be a little over 2,800 joules. Now the other option is to be looking at a phase change. So here we want to know how much energy is needed to melt the entire sample. Well, I really don't even need anything off the graph for this one. When I'm looking at melting, that's technically segment Q, and they do give me then the heat of fusion. It takes 4.6 kilojoules to melt 1 mole. Now we've got 32 grams, but we need to switch that then to moles. And it wasn't an accident that they gave me 23 grams, because it ends up being half a mole. I have half a mole, which means I need about 2.3 kilojoules of energy. Now that equation is not in the packet, but I think it's just because it's a matter of units. Whether you're dealing with heat of fusion or heat of vaporization, it's kilojoules per mole. So we just multiply that energy value by the moles that we do have. All right, here's some vapor pressure. The graph shows changes in vapor pressure as temperatures increased for 3 different samples. Which of the following correctly labels each graph? So I did kind of sketch the Lewis structures. I've got 2 tetrahedrons that are both nonpolar, but the silicone tetrahydride would have more total electrons than the CH4. So both are going to have London dispersion forces, but the silicone tetrahydride would be a little bit stronger. And then finally, my NH3 is polar. It does not have an equal distribution around the center. So it's a polar trigonal pyramid. And it does have hydrogen directly bonded to an FON. So that polar molecule is actually going to have hydrogen bonds, really strong attractive forces, which then means that segment C, which always has the lowest vapor pressure, should be my strongest intermolecular force, my NH3. Then my weakest intermolecular force would be the CH4, and that should give me the highest vapor pressure, which would be A. That's another good one. I like that one a lot. And finally, the solids. Here is a solid. It's solid silver. So that's a metal, and it's trying to show in this model the sea of electrons, that you have these positive metal nuclei, but the electrons are free to move, or we sometimes say they're delocalized, where it's not like in an ionic where the electrons are totally transferred. Here the electrons can move amongst all the positive nuclei, which then gives me the third choice down. One valence electron that is free to move throughout the metal, allowing for electrical conductivity. We'll have moving charges. It would also mean that the structure should be very malleable and ductile. I can change it from a thin wire, I can pound it into a sheet because of those non-structured electrons. They're free to move and change shape. Oh boy, here's another good one. We've got all kinds of data, and we want to try to identify what type of solid we have in unknown W, X, Y, and Z. Oh boy, so a couple things. Number one, I could easily see that the conductivity that at 25 degrees Celsius, most of them are solids, not Y. We'll deal with that one. Most of them are solids, and in the solid state, I'm seeing that Z conducts electricity. That might quickly identify Z as a metal. It's also not soluble in water. It's got a low vapor pressure and a very high melting point. That would all seem true of a metal. All right, one of the other easy ones I think is the ionic, W. Ionics are solids. They do not conduct electricity in the solid phase. So 25 degrees, when it's solid, there's no conductivity. Only when molten or when dissolved in water, because we have to have moving charges. And in that solid structure, the charges are very compact and attracted to one another. They're not going anywhere. Now it does dissolve in water then, and you would have moving charges in solution, but very high melting point and low vapor pressure, because again, those charged ions are very attracted to each other. So maybe you can easily identify W and Z as the ionic and the metallic. So then I've got the covalent network and the molecular. Well, the covalent network, that's like diamond and glass, where you've got this strong network of carbon atoms or silicone atoms in this perfect tetrahedron. It's a solid at room temperature. They do not conduct electricity because there's nothing charged. They're not soluble in water, and because of the strength of this structure, there's a super high melting point and low vapor pressure. So that might be a way to identify X as the covalent network. It's like a network of carbon or silicone. Think diamond. Which then leaves Y as my molecular solid. Molecular solids can be liquids at certain temperatures. Now here it's 25 degrees, which is relatively close to a room temperature in Celsius. And they're usually easy to freeze. Their intermolecular forces are just dependent on what type of molecule you have. So if you've got non-polar molecules, you'll probably just have weak London dispersion forces. Then it might be more likely that at 25 degrees we're still in the liquid phase. They are sometimes soluble in water, but again, because their intermolecular forces are a little weaker, they would have higher vapor pressures and lower melting points. I mean, these are probably at best, most often, London forces or dipole forces. Maybe the only exception I can think of would be water, like ice, would be a molecular solid, and it does have hydrogen bonds. All right, and the last two. Here we have an alloy, and it's an interstitial alloy, where there's a metal that has been mixed with some kind of a element that's smaller. Those smaller atoms fill in the interstitial spaces. So an example might be like steel, where you've got iron mixed with carbon. And those little carbon atoms fill in all the nooks and crannies. They make it a more rigid metal structure, so it's less malleable or ductile, and it is more dense because you don't have all those open spaces between the particles anymore. Now they're filled in by these new small atoms. And finally, here would be an ionic solid, where I have those charged ions packed and organized in this crystal lattice. If it is an ionic solid, it's going to have a low vapor pressure, high melting point. Then that's a really strong attraction, but it's not going to conduct electricity as a solid, only when molten or in solution. We need moving charges, and those charges do not move in the solid ionic crystal lattice.